Today on this channel we'll be reviewing some experiments I've conducted on trying to create ceramic strike faces with nothing more than ceramic powder and resin. So let's get started. And I forgot how insanely difficult it is to grind and sand this stuff. Hi everyone, and welcome back to the channel. So in the last video we were discussing ceramic strike faces. In particular, ceramics you can purchase at a hardware store, right? We compared 10 different ceramics and found that porcelain was the best out of all of them. And out of the porcelain, anything with a higher than a 300 break strength did really well, right? With 3 of them that were just absolutely exceptional. And as I'm currently compiling all the data for this into a PDF, I figured why not just go ahead and make another video with a project I've been working on for about 3 years now. If you're familiar with this channel, like if you've been around for a while, when I did my 1,000 subscriber special, I guess you could say, I showed these 3 plates. A polyaramid epoxy resin mix. And they made some amazingly tough plates, man. I've been playing and experimenting with this for a bit. Right, and I wanted to go ahead and show you what the test footage of those plates look like. The idea was, could I actually mix silica carbide, boron carbide, tungsten carbide, alumina oxide, right, a ceramic particulate in a resin to create a ballistic strike face? Lately I've been seeing this come up time and time again in my comment section, so it's clear you guys are curious about this as well. However, unlike some of the other projects I've done in the past, this is by no means finished. This is still in a very early prototype phase. And I generally don't like producing videos where it's just a little bit, but I have enough data for you guys this time around. And I've had other people test it on my Discord group, which has just been wonderful. This was the first project I took to the Discord group that I was like, well, I've never showed anybody this stuff. Here's some photos, some images, let's discuss it. And some of those guys actually went out, bought stuff, and went and tested it and came up with their own data and results. And they've given me permission to show you guys their results as well, which is really exciting. So let's go ahead and go over what this is and how you can make it yourself. All right, let's get started. This right here was the inspiration for this project initially. It is a steel reinforced epoxy putty. It's easy to work with, you just knead it together and it turns hard as a rock. So what I set out to do was do something similar to this but with ceramic particulates, which makes it fall into the classification of a composite rather than a true ceramic because there is glue that's holding these pieces together. And so I mixed up boron carbide, silica carbide, and tungsten carbide separately, of course, with different resins. And I measured it out by weight initially, and I'm going to talk to you guys a little bit later why that was a terrible, terrible idea. But initially what I did was I did 1-to-1, 2-to-2, and eventually 4-to-1 ratios. And once I got closer to the 4-to-1 is when it became closer to that putty and it wasn't just a thick syrup. Right, and I just pressed these into molds, and there you go. It was that simple. Let it cure overnight, and I had them. So I did some drop tests on the lower ratio ones, just to see how easy it was to break and how similar it was to ceramics. And I actually found it to be a little bit better than the ceramics, so I had high hopes. But sadly, as you'll see, it wasn't nearly as good as some of these porcelains we're talking about. Alright, so I didn't have any video of this like drop testing, mainly because it was before I got into the habit of really recording all of my experiments when it comes to, you know, the different ballistic tests that I conduct. And but I was really excited and thought that this was quite promising, you know, this 1-to-1 ratio holding together so well and actually kind of beating out the porcelain in initial drop tests. So, like I said, I ended up doing a 4-to-1 ratio, which was 4 parts of this to 1 part of this max bond resin by weight. And I did silica carbide, boron carbide, and tungsten carbide. Made their own plates. I also will talk about the grit size and particulates a little bit later. So let's go ahead and go over the footage of me prepping these to become ballistic tiles and go into the test footage of that. So some blemishes happened during the molding process. It's clear that getting a consistent plate requires you to really knead it like a dough, because once you get to such a high particulate count in the resin, it becomes impossible to truly stir. And the boron carbide one was the best out of the three, and I think it's because I started to actually knead it like a dough, like a putty, once it started to reach that limit, right? And that's definitely something, if you try it yourself, once you get past that 1-to-1 ratio, it's going to get so thick that you're just going to have to start scooping it up and molding it together. I then took and wrapped them each with Spectra cloth, which is a form of ultra-high molecular weight polyethylene. I thought this was the best way to keep the plates together while they were being shot. If I could do it over, I would just have it as a backer rather than wrapping it like this, because it became very difficult to get into those plates in order to get the the bullet fragments out once we did the testing. Alright? So, but this is just the basic setup I did for each of the three tiles in this initial test. So, let's go ahead and head out to the range and I'll show you the test footage that I did. So I didn't do any close-up footage after I shot these because I wasn't thinking, but you can clearly see the hole where it went through the clay backer and into the wood behind it and sprayed against the back face. If I had actually used a proper backer, it would have actually caught that bullet, but stupidly I had only wrapped it in the fabric. So, but this was the silica carbide one. Let's check out the boron carbide one now. Same thing with the boron carbide. Giant gaping hole in the back. Had I done a better backer, like I mentioned, we would have been able to catch it because there was a lot of bullet fragments found inside of each ceramic. And at the end of all these tests, we'll go over how we can clearly improve upon this design. Want to take a guess at how the tungsten carbide one's going to perform against the 5.56, knowing what the other two performed like? So it's clear if it had a proper backer, much like when we did these porcelain tests, right? Because when you do ceramic armor, the ceramic part only really consists of 1/3 of the total thickness of the plate. The rest of it is just trying to catch that shrapnel. Because when I started digging around through these different tiles that we shot, you could clearly see a bunch of bullet fragments, right? And as I'm looking through the clay and the wood stopper that was right behind it, that's where most of that lead and particulate. So if we had done it like this, right, just like the porcelains we just experimented with, had we done 5/8 of an inch of polycarbonate backer, would it have been able to beat out these porcelains? And the answer to that came from my Discord group, where I had some members actually experiment with this, and they got about the same results as I did. I also want to note that I did test them against the 7.62 by 39 as well. I'll show a little footage right here. Sadly, my cameras were dying, so I didn't get all of it. And at a later date, I did test it against the 357 Magnum. I was able to actually stop the 7.62 by 39 pretty much dead in its tracks, and same thing with the 357 Magnum. However, it begs the question, had we done it in a more proper way, had we approached it like traditional ceramic armor, would it have been better than porcelain? And the answer simply is no. Because there's a fundamental flaw with trying to take a particulate and a resin and making a ceramic. That doesn't mean that this method is worthless. It just means that it has a very specific use. So first, let's discuss the experiments done by some of my members on the Discord group, and then we'll talk about how we might be able to really create ceramics that are able to go way above and beyond the cheap porcelains that we can buy. Alright? Sounds interesting, right? Let's get started on that. The guy on my Discord group used alumina oxide as the powder that he chose. He had both a very fine particulate alumina oxide and a much more coarse one. And he wanted to see if he could get better object density packing in his plates by using a smaller particulate with a larger particulate. Pretty much imagine smaller particulates filling in the voids where what would be left over from the larger particulate, right? So he made up a bunch of these plates and went out and shot them, and he came to a very similar conclusion, that it just simply underperformed versus porcelain. But it was very close when we used the normal full metal jackets, but the second he stepped it up to an M855, which has a steel core penetrator in it, that went out the window. It dropped down to being suboptimal, like a 10 to 20% as effective as porcelain. So let's discuss one of the fundamental flaws in just mixing resin and particulates, and we'll also focus on how we can improve on it and what purpose this will serve in future armor. So first I want to talk about object density packing. The idea that you have a bunch of these particulates and how they actually interact with each other inside of the resin, right? So imagine these ping pong balls are grit, are particulate, right? And you put it in, you just kind of mix it up. Even if you compress it, you'll notice certain gaps and voids found inside of the mixture. That's because no matter what, it won't perfectly form a shape in there. It'll just be, you know, free floating because there's nothing really holding them together but the resin. Even if you take a smaller object and you filled the void, that was kind of his experiment, taking a smaller particulate and seeing if he could get those to fill into these void spaces. But no matter what, the main problem inherently is you take two particulates and you glue them together. Even if you get them perfectly packed into a side, into the shape, into the void that you're trying to form it into, the only thing that's actually holding these together is the resin. So you have this object that is, by all accounts, one of the hardest substances on Earth, like boron carbide or silica carbide, right? Or tungsten carbide. What do you think is going to fail when a bullet hits it? It's not the particulate, it's the resin binding these two together, right? As you can imagine, the sheer force when the bullet is impacting will break it apart. And that's what we kept seeing, is that it's underperforming versus something that is truly kilned or sintered, right? So that's what the higher end plates are. They're sintered ceramics. So let's discuss how we might actually be able to do that at home. Now that doesn't mean that there isn't a place for this as binding agents for our ceramics, you know, actually applying these ceramic tiles to a face. That would be a good spot, or where the ceramics meet up. That's where you're going to see this in the future on this channel, is trying to make a mono ceramic tile utilizing this method to help, because it's still going to be better than just a simple resin. It's just not going to perform as good as a properly sintered ceramic. So let's discuss how we might actually be able to sinter at home. So the simple explanation of sintering is using those types of particulates and mixing it with a binding agent that you plan on burning off, and it forces those little particles to actually form together and make a chemical bond between them. I didn't think this process was possible at home until I saw people start using these microwave kilns and made some remarkable things like rubies and other stuff. I'll put a link in the description to a very particular YouTuber I've seen do this, and now that I've seen him do such high temperatures with just nothing more than a microwave and one of these little kilns, I really think that we might be able to sinter or create a cement out of this and a metal particulate at home. So that's in the next few months what I'm going to be working on for this project, to see if I can actually make true ceramic tiles at home. Well, there you have it. This stuff, you know, still has some use. It would be interesting to see what would happen if we added it into like a composite, you know, like using it inside of fabric, like maybe drop down the ratio closer to like a 20% rather than being all the way up at the 67% that we're trying to achieve with the object density packing and everything. Break it back down to a closer to like a 1-to-1 sort of ratio, maybe even. That's one application. The other application would be in between the ceramic tiles, like I stated, or even behind them to just kind of increase the thickness of the ceramic. If we can sinter at home, you guys will be the first to know, because that's the direction I'm going with currently on this project. I'm going to try to make the microwave kiln and see if I can actually get some sintered ceramic and or cemented ceramic. Both will be very interesting to see ballistically, especially now that we have a good reference for the porcelain. The PDF is coming out here soon. Hopefully you guys enjoyed this. I know this is much shorter and maybe not the answer you guys wanted, but it's still data and something you can build off of, experiment with yourself, you know, grab up some ceramic particles, mix it in some resin, and maybe drop a line on my Discord and let me know how it turns out for you. Alright, and as always, please like, share, and subscribe. Suggest things you want to see me build. And if you could, like I said, subscribe and ring the notification bell, because I'm going to do something special once we hit 10,000 subscribers that I'm really excited about. So, alright guys, see you in the next one. Take care.